This short vodcast will cover factors affecting solubility and give a sample exercise in Henry's Law. At the end of the vodcast, please complete the 6 or 7 worksheet problems that are on the Henry's Law worksheet. So last year we learned that like dissolves like is an overarching axiom that chemists abide by. Polar substances will tend to dissolve in polar solvents. Nonpolar solutes dissolve in nonpolar solvents. With the exception, of course, that if you're ionic, like salt, you have a high probability of dissolving in a polar solvent, like water, because you have plus and minus charges on you, and that would be attracted to opposite charges on the water solvent. Now, in the chart below, the first thing I want you to notice is that they're all alcohols, and the first 3, starting with methanol here, is infinitely soluble in water. Then something interesting happens after we get past the 3-carbon chain of propyl alcohol, also called propanol. Now we start to see that the solubility gets less and less and less. So it's an important concept to understand that even though technically the butanol, pentanol, and hexanol are soluble in water, they become less so. The longer the chain gets, the more the molecule is duped into thinking that it's nonpolar, because that one hydroxyl group is way off at the end. If you read the fine print on the bottom of the chart, you'll notice that there's a term called miscible, and I'm not sure if we've mentioned it this year, so I want to point it out. Miscibility means 2 liquids are completely dissolvable in each other. That's generally the term that we use. Immiscible refers to 2 liquids not being soluble in each other. Now on the right column, you can see what is the solubility of these substances in a nonpolar solvent, C6H14. Seems like hexane to me. Methanol, which they all again have hydrogen bonding. Methanol is the most polar of the set because it's shortest, and therefore it would have not very much solubility in the the hexane. But then as the chains get longer and longer and longer, again, they think that they're more nonpolar than polar as the chains get longer, then you begin to see that their solubility also approaches infinity. So one other thing, fine print, down here at the bottom we haven't talked about units yet, so I want you to notice that this solubility is being expressed in moles of alcohol that's dissolvable in 100 grams of solvent, and notice that you always have to specify the temperature. Sometimes you might have grams of solute per 100 grams of solvent. Up until now, we've mostly talked about water being the solvent, but it could be a polar solvent like hexane or benzene or something like that. Okay. The factors that affect solubility obviously entail intermolecular forces. And the more similar the intermolecular forces are, then the greater the likelihood that one substance is going to be soluble in another. So if we look at the diagram on the left-hand side, that looks to me like there's 2 alcohols. I count 2 carbons in each of the alcohols, so if my little met be mnemonic, that must be ethyl alcohol or ethanol. So notice that they can do hydrogen bonding and be obviously attracted to each other. Notice that you can also have the same hydrogen bonding when there is ethyl alcohol, said it right, that's soluble in water. And again, you can have some hydrogen bonding take place. Glucose, and this is kind of a cool picture here because you get a feeling for what it really looks like, does have hydrogen bonding. And that is the picture over here on the right-hand side. See all these little hydroxyl groups out here? And these are spots where you could have hydrogen bonding. It's got 5 hydroxyl groups and is therefore very soluble in water. Cyclohexane is not going to have, or does not have, any polar hydroxyl groups. It's essentially insoluble in water. And now I'd like to kind of point out how some of these molecular shapes, as you get into the complex biomolecules or organic molecules, you can see that they try to show the 3-dimensionality. So it's not so much as a ring, and notice that there's a lot of up and down going on the bonds between the carbons, which are not shown. The carbons are at the apex, every one of those joining points of the bonds. So it's kind of an interesting thing that you'll be doing as you take organic chemistry or maybe biochemistry in college. When you look at the human metabolism, and also in many other animals, vitamin A is a nonpolar substance, so it can only be soluble in something else that is also nonpolar. Notice how complex that vitamin molecules look. Big molecule here, and yes, it has a hydroxyl group out there at the end, but because it's so big, it doesn't matter too much. It thinks that it's nonpolar. So when livestock, like cattle, are grass-fed, it will store vitamin A, cows will, in the fat in their bodies. And when you slaughter an animal, sorry, vegans and vegetarians, but when animals are butchered, if you see a lot of yellow coloring in the fat, that's because as they ate grass, which contains a lot of the carotenes, which are a part of vitamin A, that fat will get stored, or that vitamin will get stored in the fat, and it takes on a very yellow color. Those of you lucky enough to eat eggs that come from chickens that are truly free range out on grass, not on dirt, they'll have very, very bright yellow egg yolks, the fat part of an egg. Humans, as you probably know, are one of a few species, guinea pigs and other primates, that must consume ascorbic acid or vitamin C. Without it, you get scurvy. Vitamin C, as you can see, has many of these hydroxyl groups, where it can make hydrogen bonding with water, and so it's a water-soluble vitamin. Consequently, we also lack the ability to make vitamin C, so we have to constantly eat it in items that are high in vitamin C, like citrus fruits or perhaps kale is the new superfood these days. So they're very soluble in water, and if you eat lots of vitamin C, like my hero Linus Pauling suggested, a lot of times, whatever you eat, the excess just gets secreted or excreted out of your body. Gases are our focus as we come into the understanding of Henry's law. In general, the solubility of gases is going to increase with increasing mass. Now, I'm not really sure while we're talking about gases that they've given me a graphic here of sodium ions and chloride ions, but I'll take a stab at it. Let's pretend that they're gases, although I doubt this. If you look carefully at the sodium ion, you can see that it's surrounded by, let's check, starting here, counting clockwise, 1, 2, 3, 4, 5, 6 water molecules. And of course, a sodium ion is lighter than that of a chloride ion, so I'm not entirely sure why this picture is being shown. We'll let that guy go. Let's take a look at larger molecules having stronger dispersion forces. So that would be the greater the molecule, the more electrons, the greater the, what was the word, polarizability of your electron cloud, and the stronger your dispersion force. I'm not sure even why these sodium and chloride ions are there. So when you factor in the effect of pressure on substances in solution, so we've looked at the size of the molecule, and we've also talked about like dissolves in like. When you are talking about changing pressure over a solution, solids and liquids, even when they're not in solution, do not have any sort of change appreciably in their structure. But gases become very soluble if you pressurize them and force them into the liquid. So take a look at this picture too. Notice if you count the number of molecules that have been forced into solution relative to the picture above, you can see that there are way more gas molecules that have literally been pushed into the liquid. So the solubility of a gas is directly proportional to the pressure of the gas above the solvent. Now you've seen this whenever you've opened up a soda bottle that's had CO2 gas pushed into it under pressure. There's a lovely law called Henry's law, don't know who Henry is, where you can measure the solubility of the gas over here on the left by taking a constant. This would have to be given to you, and it is a constant specific for whatever solvent is doing the dissolving, times the partial pressure of the gas that you're concerned with that's over the liquid. It's really quite simple to do. So on any of these problems in this chapter, If it involves a constant on any of the colligative properties or in Henry's law, you may have to search through the textbook to find the correct table that has the correct constant for the substance that's involved in your problem. Now there's another factor which you already know about. Most substances that we've already discussed increase their solubility with increasing temperature. Greater kinetic energy is going to decrease the strength of the intermolecular forces, be able to break those down and cause these substances to go into solution, with, of course, the exception of the cerium salts. If you were to see a solubility graph that looks like this, notice that they must all be gases, because increasing the temperature will cause your gas molecules to get farther away from each other and have enough kinetic energy to break free of the liquid phase. Examples of this would be letting a soda sit on the counter and watching it go flat. Also, if you're a fish in water that's very warm, the amount of dissolved oxygen is less, and therefore there are issues with anoxic conditions or anaerobic conditions in lakes that don't have enough dissolved oxygen. By the way, I just wanted to point out over here that on the units of solubility on this graph, there's a little m with a big M, and that's called millimoles. It's just a thousandth of a mole, and it must be per some unit of either grams or some other unit of volume, perhaps, for gases in a liquid. So let's do this simple Henry's law calculation, and then we're done. Very easy. You're asked to calculate the concentration of carbon dioxide in a soft drink that is bottled with a partial pressure of 4.0 atmospheres. So the CO2 over the water is 4.0 atmospheres. They give you the temperature, which they have to specify, because the Henry's law constant for CO2 in water at that temp is in moles per liter atmosphere. So we have our two values. We find our equation. The concentration, or the solubility of the substance, is equal to the Henry's law constant times the partial pressure for that particular substance in water at that temperature. So the values that we plugged in have all been given to us. Notice that moles per liter atmosphere will cancel out atmospheres. That first atmosphere right here is in the denominator. This is in a numerator, and so those two atmospheres will cancel. Our answer will be given in moles per liter, which we know as molarity. And we went to 2 sig figs because there were 2 sig figs in each of the questions, or each of the bits of data that were given to us in the question. Essentially, that's it. You now have a worksheet to complete, ready to turn into class at tomorrow's first of the period. And as you notice, we will be going next into ways of expressing concentration on a quiz on Friday. We've already discussed molarity, molality, mole fraction, and percent by mass. So be prepared to answer a question of how to calculate concentrations 4 different ways. Until next time.